Hello, and welcome to Linear Algebra. This is lecture 12, and today's topic is kernel and range. So last time we talked about the LU decomposition of a matrix. So this is about solving systems of linear equations, AX equal to B. You decompose the matrix A into L times U, and then it's very quick and easy to solve the system. Okay, this time we're going to be talking about something of a somewhat different flavor. We're going to be talking about some subspaces associated to a linear map. Okay, so let V and W be vector spaces over a field F. Every linear map from V to W has associated to it two subspaces. One a subspace of V and the other a subspace of W. So we have the kernel of T, also known as the null space of T, which is inside V, and we have the range of T, which is also denoted T of V, which sits inside W. Okay, so the kernel of T is char T, all of the vectors in V, such that T of V is equal to 0. And so all of the vectors that T sends to the 0 vector. Right? So this lives inside V. Okay, and now let's check that this is a subspace. V. So first, we need to check that it contains the 0 vector, right? But T of 0 is 0, so that means that, so notice that here, this 0 lives inside the vector space V, and this 0 sits inside the vector space W, right? So the kernel of T are all of the vectors that T sends to the 0 vector in W. And this equation shows that the 0 vector in V gets sent to the 0 vector in W. So this tells us that the 0 vector in V is inside the kernel of T. Okay, next we need to check that this subspace, this subset, is closed under addition and scalar multiplication. Now, when we talked about checking that a map is linear, I pointed out that linear is the same as taking linear combinations to linear combinations. And so you can check that the two properties, linearity and homogeneity, hold at the same time by just considering a linear combination of two vectors, and you only need one scalar. The same is true for a subspace. So I'm going to check both that it's closed under addition and that it's closed under scalar multiplication at the same time by checking that if V1 and V2 are arbitrary vectors in the kernel and C is an arbitrary scalar, then, okay, well, let's consider V1 plus C times V2. T sends that to T of V1 plus C times T of V2. T of V1 is equal to 0. T of V2 is equal to 0. And so altogether that gets sent to 0. So that shows that V1 plus C times V2 is in the kernel. Okay, now we needed to show that it's closed under addition, right? But take the constant c to be equal to 1, and we've just checked that if v1 and v2 are in the kernel, then v1 plus v2 is in the kernel, right? And then we need to check that it's closed under scalar multiplication. So take the vector v1 to be 0, right, which we already know is in the kernel. Take v1 to be 0, then we've just checked that if v2 is in the kernel and c is an arbitrary scalar, then c times v2 is in the kernel. So we've checked that it's closed under scalar multiplication. So by using this linear combination and checking that anytime you have two vectors in the subset and any scalar that this linear combination is in the subset, we've checked that it is a subspace. Okay, so that's the kernel. Let's give a similarly formal definition of the range. So the range of T is, so we'll either write out range of T or write it as T of capital V. This is all of the, well, it's all of the vectors T of little v such that little v is in big V. Right? And so it's a subset of W, and we will now check that it is a subspace. Right? So this is a subspace of W. Okay, so we'll just check the same two things. First, so I'm going to write the same equation, T of 0 is equal to 0, but whereas before that showed that the 0 in V was in the kernel, now the same equation tells us that the 0 of W is inside the range. Right? So the range of T are all of the vectors that are in the image of T, all of the vectors that are equal to T of V for some V. So 0 is equal to T of V for some V. You can take 0 as that V. Okay, and secondly, let's take two vectors, W's. If W1 and W2 are in the range of T, and C is an arbitrary scalar, I want to check that the linear combination is in the range of T, right? So let's start with what we know. So W1 is in the range of T, so W1 is equal to T of V1, and W2 is equal to T of V2 for some vectors V1, V2 in V. Okay, so if I write W1 plus C W2, if I take this linear combination, I can write W1 as T of V1, and I can write W2 as T of V2. So let's do that. And now we're going to use the fact that T is linear to write this as T of V1 plus C V2. Okay, now this is some vector in V. So this is T of some vector in V. Right? So this shows that W1 plus CW2 is also in the range of T. Right? And that's what we want to check. Okay. So now why are these subspaces interesting? Well, for example, notice that T of V1 is equal to T of V2, any V1, V2 in the vector space V. Well, this is the same as saying that T of V1 minus T of V2 is equal to 0, right? And because T is linear, that's the same as saying that T of V1 minus V2 is equal to the vector 0, right? But we now have a different way of saying this. We could say that V1 minus V2 is in the kernel of T, right? So, okay, here is one immediate consequence. T is injective, right? Injective is another word for one-to-one. Incidentally, one-to-one is a terrible phrase, right? Every function sends one thing to one thing. What we want to say with injective is that different elements of the domain get sent to different elements of the range. So really, it shouldn't be called one-to-one. It should be called two-to-two, because that's what you're trying to say. But in any case, the word injective is better. I think it's better because of that. Okay, but hence T is injective if and only if the kernel of T has only the element 0. Okay. Another place where the kernel comes up a lot is when we're talking about eigenvalues and eigenvectors, right? So let's say that V is equal to W, right? And T is a linear map from V to V. Then V is an eigenvector of T with eigenvalue lambda. Well, by definition, remember that means that V is not the 0 vector. And T sends V to a multiple, to lambda times V. Okay, another way of saying that is that V is not the 0 vector, and T minus lambda times the identity sends V to 0. So now we have another way of saying this. V is not 0, and V is in the kernel of the linear map T minus lambda times the identity. Okay, so we give this kernel a name for each eigenvalue, lambda of T, eig sub lambda of T is the kernel T minus lambda I, and is called the lambda eigenspace of T, right? So because it's a kernel, it is a subspace. So it is a subspace of V consisting of the 0 vector and the eigenvectors of T with eigenvalue lambda. Okay, great. So that's a couple of things about the kernel. Now let's take a look at the range. So for example, what if you have a linear map that's working by matrix vector multiplication? What is the range? So proposition, if T is a linear map from Fn to Fm, and it is represented by the matrix A, so an m by n matrix, then the range of T is equal to the span of the columns of A. Okay, so let's prove this. Okay, so if we write, let's write the matrix A like this, and let's give the columns names. So they're just going to be lowercase a1 through an. Okay, then each aj is just T of ej, right? So remember, we talked about how you can find the columns of the of the matrix representing a linear map easily, one column at a time. You just use the standard basis of Fn and plug it into your linear map, and you'll just get each column, right? So T of Ej gives you the column Aj. And that shows that Aj is in the range of T, right? The range of T is all of the things that I can write as T of something, and I've just written the column Aj as T of something. Now, since the range of T is a subspace of W, and it contains these vectors, the AJs, then it has to contain all of the linear combinations of these vectors, and that's the span. So this implies that the span of A1 through AN is inside the range of T. Okay, on the other hand, right, so that shows one inclusion. We know that the span of the columns is inside the range. Now I want to check that the range is inside the span of the columns. So let's pick anybody in the range and let's show that it's in the span of the columns. So if W is a vector in the range of T, then W is equal to T of V for some V, and let's go ahead and say that its coordinates are V1 through Vn. Right, but then W is equal to A times V, right, because A is the matrix representing the map T, and if you do A times a vector, well, remember that one of our interpretations of matrix vector multiplication is that this is the linear combination of the columns of A with coefficients Vj. So in particular, this is an element of the span of the columns of A. That shows that the range of T is a subset of the span of the columns. Okay, so that proves the proposition. The range of T, when you're going between Fn and Fm, is the same as the span of the columns of the matrix representing T. Right, so we give that a name too. The span of the columns of A is called its column space. Very original, of course. And we denote it C of A. We also talk about the kernel of A as being, or the null space of A, as being the kernel of the associated linear map. So it would be all of the vectors that get multiplied by A to the zero vector. Okay? So everything ultimately comes down to systems of linear equations. So what does this tell us about systems? What do these spaces tell us about systems of equations? Okay, well, first of all, Ax equal to B is consistent if and only if B is an element of the column space of A. It's a linear combination of the columns if it's equal to A times X. Okay. In particular, here's a nice fact. A list of vectors should say a set of vectors, so I don't care about the order. A set of vectors inside Fm spans all of Fm if and only if the reduced row echelon form of the matrix A that you get by just putting these vectors as the columns of a matrix has a pivot in every row. Okay, so let's prove this. Right, so I want to know if I span all of Fm. Right, so let's see, what do we know? What are some easy facts? We know that the span is equal to all of Fm if and only if the column space of A is equal to Fm, if and only if for every B, for every B in Fm, we can solve AX equal to B. Okay, so that's what we know from the discussion right here, right? That AX equal to B is consistent if and only if B is in the column space. Okay, on the other hand, now let's use our Gaussian elimination algorithm. So we know that you can solve AX equal to B precisely when the reduced row echelon form of the augmented matrix never has a pivot in the last column. Right? If you can solve this for every B, that means that this augmented matrix never has a pivot in the last column. Okay, now the only way you can guarantee that no matter what you put here in this column, the reduced row echelon form does not have a pivot in this column is if every row, because remember each row has at most one pivot, every row already has a pivot without using B, right? That way you're guaranteed that no matter what you put here, it will not get a pivot when you go to the reduced row echelon form, right? And it's an if and only if, because if there is a row here of A that the reduced row echelon form does not have a pivot, then I can just put a B so that when I get to the reduced row echelon form, it has a non-zero entry, and that'll be a pivot. So this happens if and only if the reduced row echelon form of A has a pivot. In every row, and that's exactly what we wanted to check. In particular, here's something that you should be expecting. This is very intuitive, but it's something that we hadn't shown until now. So one consequence is that if the span of the vectors v1 through vn is equal to fn, then n has to be at least as large as m. Right? If you're going to span R3 with some vectors, you're going to need at least 3 vectors. Okay, so that's the first thing that we know about systems of equations. If AX is equal to B is consistent, then B is in the column space. Okay, now, so that was information about the B. Now, what do we know about the X? Right, so secondly, if AX equal to B is consistent, so that means that there is a solution, then any 2 solutions differ by an element of the kernel of A, which, as I mentioned, is the same as the kernel of the linear map multiplication by A. So this would be all of the vectors so that A times V is equal to 0. Okay, so let's check this. So it's the same as for a linear map. So if here you have x1 and x2, and these are vectors in V that satisfy ax1 is equal to b and ax2 is equal to b, then A of multiplying x1 minus x2 is equal to 0, which is the same as saying x1 minus x2 is an element of the kernel of A. Okay, so if you find one solution, of ax equal to b, then we can express the set of all solutions as, let's use S for solutions, S, which would be x naught plus V, such that V is in the kernel of A. Right? Or with some abusive notation, we might write this as x naught plus the kernel of A. Right? Which is a bit of abusive notation, but it's just a faster way of writing this. Okay, now if B is equal to 0, then of course this is just the kernel of A, and that is a subspace. If B is not equal to 0, then S is not a subspace of V. It is very close to a subspace, so we give it a name. It is an affine space. I.e., a translation of a subspace. In fact, of the subspace kernel of A. Right? So you're taking this and you're translating it by a fixed vector, by any particular solution. So let's do an example. So last time, we found that if A is the matrix with columns 3 minus 9, 15, 3, 1 minus 1, 9, 9, minus 5, 14, minus 23, minus 9, 2, minus 5, 12, 7, 0, minus 1, 2, 1, and B is the vector 4, minus 10, 20, 13, then the solutions to AX equal to B make up the set S. So we have minus 1, 0, minus 1, 1, 0, plus T times 5 over 6, 5 over 2, minus 1, minus 5, 1, where T is an arbitrary real number. All right, so we found that last time using the LU decomposition of A. So now looking at this set S, we see that here x naught, this vector minus 1, 0, minus 1, 1, 0, is a particular solution. Right? It's the particular solution I get by setting t equal to 0. Of course, I get a particular solution by picking any value of t. but in particular, that's one of them. And the kernel of A is the span of this other vector, 5 over 6, 5 over 2, minus 1, minus 5, 1. Right? This vector spans the kernel of A. Right? And so this set of solutions is of the form that we're just talking about, a particular solution plus elements of the kernel of A. Okay, let's do one more example. Let's say we want to find the eigenspace of the matrix A. So let's do a 3 by 3. 7, 0, minus 6, minus 2, 1, 2, 4, 0, minus 3. Corresponding to the eigenvalue lambda equal to 1. Okay, so we're looking for Eig1 of A, which would be the kernel of A minus 1 times the 3 by 3 identity. Right? So this would be the kernel. So A minus the 3 by 3 identity just means take the matrix A and then subtract 1 from the diagonal. Right? So that means I end up with 6, 0, minus 6, minus 2, 0, 2, 4, 0, minus 4. Okay, so we're looking for the kernel of this. That means we're looking for all of the solutions of Ax equal to 0, where instead of A, we're going to use A minus 1 times the identity. Right, so since we're trying to solve that, what we should look at is the augmented matrix 6 minus 2, 4, augment 0, 0, 0, 0, 0, minus 6, 2, minus 4, 0. So putting this into reduced row echelon form, we get the matrix. So the first row would be 1 minus 1/3, 2/3, 0, and everything else is going to be 0. Okay, so we're solving A minus 1 times the identity times x equal to 0 by using Gaussian elimination, form the augmented matrix, put it into reduced row echelon form, and then translate back to a system of equations. So this translates to the equation x minus 1/3 y plus 2/3 z is equal to 0, right? Now, notice that here x is a pivot variable, y and z are free variables. Right, so the solution is to set x equal to 1/3 y minus 2/3 z, right? So you want to write the pivot variables in terms of the free variables. Okay, so now thus the set of solutions is, okay, so this set of solutions is called the eigenspace of A corresponding to eigenvalue 1, so Eig1A, and so it's going to be all of the x, y, z, where x is 1/3 y minus 2/3 z, y is just y, z is just c, right, which I can write as y times 1/3 1, 0 plus c times minus 2/3 0, 1. And here y and z are arbitrary real numbers. Right? And I can write this just by looking at it. We see that this is the span of the vectors 1/3, 1, 0, and minus 2/3, 0, 1. Okay, so there we go. The eigenspace, and we've written it as the span of these two vectors. Notice these are obviously eigenvectors corresponding to the eigenvalue 1, but so is any linear combination of them that's not the 0 vector. Okay, we'll stop there for today and pick it up there next time.